So let's get started. Welcome back to lecture. Is this 7 or 8?
6 because you didn't have a lecture 6.
But yes, week 7 of deep unsupervised learning. So what we will do today is we will spend probably 2/3 of the time talking about more GANs, and then we will spend some time talking about non-generative based unsupervised learning methods. Questions on like logistics and high-level stuff?
Question about project?
Yeah.
Do we get any AWS credits for the final project?
Do you get what?
Do we get any AWS credits for the final project?
So
We got 4 each for 130.
right. So if you were careful in using that, you should still have some spare that's left. I don't think we have planned for like dedicated project credits yet. We will see. Cool. So far we have learned about autoregressive models, flow models, and latent variable models. And all of them really fall under this likelihood-based framework. Like either you have explicit tractable likelihoods, or in the case of latent variable models, you don't have the explicit likelihood, but you can still use variational inference to get a bound of the likelihood. But GAN is really a very different animal in the sense that you don't really get any likelihood evaluations. And really what you train is you train some deterministic function that maps certain noise variable into some data space. And you don't know the prescribed likelihood, and you don't really have other access to the models. And really the only thing you can do with the model is to basically sample from it. And now we essentially require a training regime where you can actually train this thing just by looking at its samples without doing anything else. So that's within this implicit generative models framework, GAN is the most popular one, the one that most people know. So that's what we would talk about and, well, more like recap. So we'll skip through a lot of them. So GANs is, I would say like probably most people know generative models by GANs, like rather than knowing it by some other discipline. So it has really popularized, call it this domain. And this is again just recap. And the core idea of GAN is you have sort of a two-player game. Instead of like training one generative model, like you train one generative model and then you also train a discriminator. And the job of the discriminator is to try to say what data points are more likely to be real and what data points are more likely to be fake. And then you can essentially derive a gradient direction from how probable your discriminator thinks the data point is. And this is again just to walk through the schematic of what we are doing here. Essentially, on the left is the discriminator. What it tries to do is basically take in each data point and then try to predict a score that says whether this is likely to be fake or likely to be real. And in the original GAN framework, like we formulate this as a classification problem, but it really doesn't need to be a classification problem. Just think of it as a certain score that you want to have higher score for real images and lower scores for fake images. And then the job of the generator would be taking in some noise. You map it through some differentiable function, and then that becomes your data point. And then that would get fed through the discriminator, and then you would try to fool the discriminator. You would try to generate data points that achieve a high score under your discriminator score function. Questions so far? And what I would like to do today, you have seen all the math, the derivation, what is the optimal discriminator and things like that. What I would like to do today is, instead of going through the derivation or the maths, I would like to take a more intuitive look at what is actually happening in this two-player game. And someone make a really nice in-browser training, GAN training framework. So this, again, you can play with on your own laptop as well. And so what is being shown here is that the green dots are all the real samples. And so you can see it's kind of an elongated Gaussian plus a more standard Gaussian. So it's a mixture of these two distributions. And all the purple points are basically points that are being generated by your generator. And what is also plotted here is a gradient direction that would increase the score for a particular data point. So let's say if we look at this one, then when the purple vector is pointing into this direction, that means the discriminator is telling it that if you move into that direction, you would increase your discriminator score the most. So that is the core of the training dynamics of a GAN. So you basically generate a bunch of random guesses. And then based on those random guesses, you hope that your discriminator can push you into the direction of being closer to a real distribution. And the discriminator's job would essentially be continuously trying to spot in what region it's more likely to be fake, and in what region it's more likely to be a real images. And what we also see here is kind of typical of GAN trainings, where you see a lot of oscillations, and it really takes a while to converge to something that looks like a true distribution. And even when after it has converged, if you train it for long enough, it could still collapse. And then we have been training this for a while, and then you can see that some of the gradient directions are really totally off. Let's say for some of the purple dots that are here, it's trying to point to the top right corner. But this is not really the right thing to do, because we know real data doesn't really distribute significant probability mass into that direction. But why does it do that? It does that because the discriminator is telling it to do that. But you don't have a perfect discriminator. So and that is why this kind of model is always very delicate, in the sense that your generator is learning from called a score function that is not perfect. And at the same time, the score function cannot be too perfect, because if the score function is perfect, and let's say we're looking at some kind of truncated Gaussian distribution that has no support in certain regions of your data space, then if your generated samples land on there, then it would never get any meaningful training signal. So in all kind of GAN architectures design, you are trying to balance these two things. You want to have a discriminator that is as correct as possible, otherwise it would just point you into a wrong direction. Yet at the same time, you want to regularize it enough that even when you're far away from correct data distribution, it still gives you meaningful signal. Questions? Want to see more? Here you really see the oscillation of it. Originally it was too concentrated in the middle. By the way, when we look at this kind of low-dimensional data, it's really not doing GAN its justice. If for this kind of data, if you just train, let's say, an autoregressive model or a flow or a VAE, it can learn this in under a couple minutes, and it would make stable progress towards there, and it would never diverge. And unlike this kind of chaotic dance that's being performed by GAN. But really where GAN really shines is in high-dimensional data, especially in images. When you couple that with a convolutional generator and discriminator, it does magic. And I don't think anyone really know why that is the case. But just want to say that, like, seeing bad performance of GAN here, it's sort of expected in low-dimensional space. Cool. So these are some of the original GAN samples from the initial GAN papers. You can even argue that they are not that different from some other generative models in that kind of years. But one thing that's make this model pretty unique is it's fairly difficult to evaluate this model. Let's say I propose this GAN model, and then I look at these images. Like, what can I tell of these images? Like, it's really hard to say that, like, these are much better than some other models because you don't really have a good way to evaluate it. So part of what we will spend this lecture on is talking about how to evaluate implicit generative models like GANs. We will cover some of the methods, but this is still pretty much an open problem. Like, there's no known good way to measure GAN quality or any implicit generative model's quality that has no obvious drawbacks. So we would look at some prevailing methods that people use to evaluate GANs, but they all have their own drawbacks that we will point out. And this is also to just give you the knowledge to kind of read new GAN papers. Like, how can I say that this new GAN loss, this new GAN architecture actually gives you something substantially different? So in the initial GAN paper, the method or the model was evaluated by this method called Parzen-Window density estimator, or it's also known as kernel density estimator. And the premise here is I have some known data points that come from this distribution, and I can build a density estimator condition on those known data points. And then I can treat that as a estimation of what, let's say I take n data points from my GAN generators. And then I can feed those n data points into a kernel density estimator. And then that would in turn give me a non-parametric density function. Then I would evaluate that non-parametric density function on test data. And then I can report certain test generalization density metric. And the typical way that this is done is you would have, so let's say this is my guess. Let's see. This is my guess of the density function. And then I would take n data points to create this density function. And what it does is it really just loops through n data points, and then it creates a probability mass around each data point. And then k, the kernel function, is usually just the density function of a standard normal distribution. So if you think about what it's implicitly doing, is that for each point that is close to the n data points that I have, I would give it high probability mass. For anything that is far away from it, the probability mass decays rapidly. And you essentially imagine this to be a high-dimensional space where you have small Gaussian bumps at a lot of places that your generator has generated samples for. So that's the kind of the oldest method to evaluate GAN results. And also, if we look at this equation, there's another hyperparameter that we did not talk about, that is h. So h is usually called bandwidth in this kind of kernel density estimator parlance. And the bandwidth h really matters, because if we think about what it is doing, bandwidth h sharpens or dampens your the probability mass that you put around each known data point. So if I choose a very small h, what it means is that I only put probability mass exactly at the data point that I know that is generated from the model. And if I choose a higher h, and then it will have a larger smoothing effect. And we can see that here. So what is being shown here is the graph curve is the density of a normal distribution. So this is just like what the ground truth is. And then what we can do is we can generate a bunch of samples from this standard normal distribution. And after I generate a bunch of samples, I can use those samples to create a kernel density estimator. And then now what we vary is we try to use different bandwidth parameter to create different kernel density estimator. So what we can see is, let's start from the last one. From the orange one, if we choose a very small bandwidth, recall what that would do is it would put very peaky probability mass around known data point. And then you get a density curve that looks like this. So it should have it definitely sees a sample here, it has a sample here, it has a sample here, it has a sample here. But instead of like interpolating these points into a smooth curve, what you would do is you would put very high probability mass close to a point that you see, and then have sharp decay from there. And as you can see, this orange curve is really a large deviation from the ground truth gray curve. And then as you increase the bandwidth, you make the curve smoother and smoother. So if we look at the green one, it's a lot smoother, a lot less high frequency fluctuation than the orange one. And then if you look at the blue one, it's actually pretty smooth and tracks the ground truth density pretty well. And the way that Parzen-Window density estimator or kernel density estimator is used in GAN evaluation is that you essentially have a validation set, and then you would basically choose your bandwidth hyperparameter based on validation score. So you try to find a bandwidth parameter that maximizes the density results on the test set data. Questions on the mechanics of this method? Yes?
So do we want it to be like, would we be able to tell without just doing hyperparameter circle, whether we want it to be spikier or like more spread out? Or does the shape, like you wouldn't even care about the shape, you would just choose whatever gave you like the best results?
So the question is there a principal way to choose H by saying, I want this to be this spiky, I want this to be this spread out? So unfortunately, there's no good way to do that without making assumptions on your underlying data. So if you know what my underlying data is, then you can probably choose the H in an optimal way. But then that kind of defeats the purpose. But if you already know the underlying distribution, then there's no point in estimating that from finite data from the first place. Cool. So these are just some of the results that are pulled from the initial GAN papers. And what they were shown here was essentially GANs achieve competitive density modeling results if you assume these estimators are accurate. And we'll take a look at why some of these are hard to interpret. This is not to say that the initial GANs were not as good as some of the others. They probably were much better than some of the others. But it's just very difficult to read that result from just a kernel density estimator. So this kind of estimator can be really unreliable. So we are showing two cases of where it can be problematic. On the left, we can show that it's incredibly difficult to use this kind of non-parametric estimator to get to ground truth log likelihood or density. So what is being shown here is that for a distribution, what you try to do is you try to increase the number of samples that you used for this kernel density estimator. So, and this is on log scale, so this increases quite drastically. And this black line here is the ground truth density. And what you would hope to see is that as you increase the number of samples, you approach ground truth density very rapidly. But this is not the case, especially in high dimensional space where even if you put a bunch of Gaussian bumps on it, there are still plenty of spaces that you don't cover. And you really need a lot of samples to fully cover the space. So for one thing, like it could be highly grossly underestimating the underlying probability. And then the second dimension is this table is pulled from this paper, A Note on Evaluation of Generative Models. And they essentially constructed a pathological case where kernel density estimators would actually give you higher score than ground truth. So what this means is that this kind of estimator can not just underestimate, but it can also grossly overestimate the performance of the model. And some of this come from the fact that it assumes a certain kind of continuous distribution, and if the data that you're modeling is really not continuous, then it could have rather arbitrary things happening. So people in the field also understood the limitations of this kind of kernel density estimators. And that's why in the past couple years, people have been moving away from it. If you look at the newer GAN papers, they typically no longer report this score. So any more questions on kernel density estimation? Cool. So after this kind of attempt to estimate density in high dimensional space, people have looked elsewhere to find a good way to measure how good is your generative model. So one of the ideas that is proposed in the improved GAN paper is a good generator should generate samples that are semantically diverse. So let's unpack what does that mean. So that means if we have a good generators, then it should generate a lot of distinct images. But how do you measure distinctness? Like you can't just say these images are distinct in RGB space. So we say that these images are distinct in semantics. Like they correspond to different classes of objects. They correspond to different type of scenes. So in this particular construction, what people did is they took a pre-trained Inception network V3 that is trained on ImageNet classification problem. And essentially what you get is you get a neural network that takes in an image and then gives you a probability distribution over classes. Like basically what class does this object, does this image belong to? And here y given x, y is one of the 1000 ImageNet classes. By the way, it's like really random in case you have not looked at ImageNet classes before. These are the classes. Like, I mean, honestly, I think I would do extremely poorly. Like, I have no idea what is a English setter? Sea lion? Anyways, so basically this is what the semantic predictor is trained on. So basically, the Inception network should take in an image and then say how likely it is to belong to one of these 1000 categories. And there are a couple considerations. So if we take this inspiration and then make it more concrete, then there are two criteria. One criteria is each image should have a distinct object, because most of our models are trained on images that only contain one object. So if our generator is good, then it should generate images that you can see distinctly there are objects in it. So if you see an image, you should be able to say that this belongs to a certain class with very high confidence. And probabilistically, what does that mean is this conditional distribution, y given x, should have low entropy. That means after I see an image x, I'm very certain what class does it belong to. And then the second dimension is there should be as many classes generated as possible. So if I have a generator that's trained on all ImageNet, but it can only generate cats for me, then like you can say it's a great cat generator, but it's not a very good general generator. So you also want it to be able to generate as many classes as possible. And we encapsulate that by saying the marginal distribution of predictive label should have high entropy. So mathematically, this is what it means. What it means is that we are given an inception model. And again, this is just a model that is trained on ImageNet. Like we don't really train this part. This part is given to us. And then after I have this conditional distribution, I would use that to define a marginal label distribution. And then the way that you do that is you sample a bunch of points from your generator, which we know how to do. You just sample a bunch of points from your noise distribution, and then you map it through your generator. Now you get a bunch of generated samples. And then you would evaluate this conditional distribution, and then you would average that. So that gives you the marginal label distribution. And then what the inception score is simply, we can ignore the exponential for now. It's simply you generate from your generator, and then you evaluate a KL divergence. And the KL divergence is simply the KL divergence from your conditional label distribution to the marginal label distribution. And then you sample a bunch of times, and then you take average of that KL divergence. And then you take average of that KL divergence. And after you take the average, you take an exponential of that for easier to compare. And that's the so-called inception score, which you will find a lot in kind of modern GAN architectures and methods, and they use this to compare. But you might say like this way of writing the inception score is rather cryptic. Like it's not very clear what it is actually doing. Like you are trying to generate a bunch of samples, and then for each sample you measure the KL divergence, but then like what is this actually doing? So what it is actually doing is actually has a really nice intuitive interpretation. So if we go from this line to the second line, where we simply expand the definition of KL divergence, we get something like this. Right. So what we can notice here is that the second term is simply the marginal entropy of y. All right? Because we are generating x, and y comes from the conditional distribution of x. So you can see this as generating from basically the definition of above. So what this corresponds to is, this corresponds to the entropy of y. And then the first part corresponds to the conditional entropy of y given x. And what this boils down to is an equation like this. And it actually measures, so basically what it measures is the entropy of y subtracted by the conditional entropy of y given x, which is exactly what we talked about in the slide before. Like you want entropy of y to be high so that your model generates a lot of different classes. And you want the conditional entropy of y given x to be very low. And that means after I see the x, my label predictor is very certain. And that is basically all this is measuring. It's trying to measure how semantically diverse my generator is, and also within one image, how distinct it is. And it has another interpretation that is the mutual information between x and y, but we will not go into that. Was the mechanics of it clear? Yep.
So for P y given x, so that's predicted by the predictor.
Yeah.
Do we need a very accurate predictor?
Yeah. So the question is, to evaluate this correctly, you need P of y given x to be very accurate. Like otherwise, if I give you a cat, but if your predictor cannot tell, like it actually predicts something that is high entropy, then it will be wrong. So the answer is yes. So the kind of implicit assumption here is that a model that is trained, like an inception model that is trained on ImageNet is good enough, but then like it's really hard to evaluate whether it's actually good enough or not.
So it has an assumption like the data set the synthetic data set you generate, like it should be similar with the ImageNet.
Yeah,
so
that's
if you generate something like a medical image, that's totally different with the
yeah.
cats and dogs. So
yeah.
this cannot apply.
Yeah. So the question is, since we use an ImageNet classifier, then that means like the kind of measure of semantic diversity is implicitly defined within the scope of ImageNet classification. So if you have a very different problems like medical images or some other images, then Inception Score no longer applies. So the comment is correct. Like it's no longer meaningful to do anything like that. And in fact, like the most common ways to use this score, I would say like it's not totally valid either. Like most of the times this score is used when you train a model on say CFAR10. And then you evaluate on ImageNet classes. Like you can say that ImageNet classes is a richer definition of the semantics, but there's still a certain shift that is not like totally just modeling how well you can generate CFAR10 classes. Like it's measuring something that is somewhat different. Cool. So these are some of the this is a table taken from the improved GAN paper. And what they're showing is different variants of GANs and the inception score that they achieve. And what we can see is that like for certain GANs that are worse in terms of like there's no distinct objects in it and there's not very semantically diverse, then it gets a lower score. And then for a GAN that is better in terms of being able to fit images, being able to generate images that are fairly distinctly look like some kind of objects, like this horse, look like a horse, this looks like a ship. And for this kind of generator, it gets a higher inception score. And of course, ground truth does better than this. Yes?
So the inception score is not a component of the loss, it's just a metric that we use to evaluate the models, right?
Yeah, so the question is the inception score is not a component of the loss and we only use it to evaluate. So that is correct. And it's actually very crucial because if we optimize on inception score, actually anyone would guess what would happen? Yes?
The generator will basically learn like adversarial example kind of things
Yeah.
for every category.
Yeah.
And then just
Yeah.
randomly sample.
Yeah. So that was exactly what I was looking for. So if you actually optimize on the inception score, it would not give you the correct thing. Like most likely, it would find some adversarial patterns.
So the follow-up is then our generator is really likely to just generate examples that fool the discriminant. So
Right.
if it's true that the most fooling examples aren't actually semantically diverse,
Yeah.
then aren't we going to be like, is it fair to punish it for that?
So can you repeat the question?
The discriminator is able to distinguish fake and real between like 990 of the image classes.
Mhm.
But on the remaining 10, it has no idea what to do, it gets
Mhm.
completely fooled by the generator.
Mhm.
Then it seems that the generator would
Right.
probably say, okay, let me just generate
Right.
something that's like this.
Right.
We're punishing it for doing that.
Right. So the question is a great one. So the question is, let's say my ground truth data does contain 1,000 classes. And let's say I'm trying to fit a GAN to those 1,000 classes. But for whatever reason, my discriminator cannot distinguish among some classes. And that is possible. Let's say there are some classes that rely on like maybe it needs to have a certain specific architecture to detect it, but my discriminator doesn't have that architecture. Then essentially your GAN training mechanism would have no supervision or training signal for your model to capture those classes. And as such, like your model would get penalized in this inception score. But that, in a sense, is to be expected, because if your discriminator is not good enough, that causes your generator to not be good enough, and then it gets penalized by this score. More questions on inception score? So the next one is sort of the latest addition to the mix. So inception score is okay, but one example of the weakness is that like it doesn't really sufficiently measure diversity, due to the fact that you are just measuring mutual information between X and label Y. It's essentially bounded by however number of bits that your classes have. And a concrete example of like how you attack that is, say, if I have a list of images, let's say I take one image from each of the ImageNet classes, and I just treat that list as my generator. And now that list could obtain perfect inception score, right? Because for each of my image, my classifier is going to be confidently say this belongs to class something. And then I have 1,000 different classes. Then that means I maximizes the diversity measure under inception score. And of course, like it's not likely to actually get a generator that looks exactly like that. But that also implicitly say that you could actually have a generative models that are not very good, but still achieve very high inception score. And the essence of this is because it's only trying to capture the label distribution and then use the label distribution as a way to compare the generators. And this, I will not attempt to pronounce this. And FID is proposed to capture more nuances than that. And what it is trying to do is it's trying to say, instead of comparing distributions based on only the conditional label distributions, what I would do is I would try to compare different distributions based on certain semantic features. And mechanically, how they do it is you say for each image that's generated by your generator, I would feed it through some network and then transform it into some feature space. And hopefully this feature space has good semantic meaning. And the choice that's used in the community is you again take the Inception V3 network and then you take the POL3 layer, so which is a 2000 dimensional activations. You treat that as your kind of feature embedding space of the image. And then what you would do is you would sample a bunch of points from your generators, and then for each point you map it through this embedding. And then you would compute the mean and covariance of those embeddings. So you can also think of it as you're fitting an empirical Gaussian to all those embedding data points. So now you have one Gaussian that is for the generative samples. Then you also generate a bunch of points from the validation set of your training data. So now you can actually construct another multidimensional Gaussian from data that your model has never seen. And then what you would compute is you would basically compute a distance metric between these two Gaussians. But I mean, since they are not Gaussian in the first place, it's kind of arbitrary. But really, just think of it as how different are your are the means and covariance from your generator? How different are they from the means and covariance of the ground truth data? Yes.
And this is done like per Oh, okay, just across all the data points.
Yeah. So, well, you do it on validation set data. So you basically you do this procedure for some validation set data, and you also do this procedure for a bunch of generated data, and then you compare how similar or dissimilar are they from each other.
We could still have a bunch of dissimilar images that could like resemble like the same class.
Well, I mean, in this case, there isn't even a class definition. So you just take some pre-trained network, and then you take some of the features, and then you hope the features are good.
I see.
But in a sense, it's also richer than just taking the classes labels, because you can imagine that the two images that map to the same class will still have very different intermediary neural net activations. So this is trying to capture those additional details. Cool. So in the paper that proposed this distance, this evaluation metric for GAN, they also did some pretty interesting evaluation. They basically they take a good image, and then they compare what would happen. They basically propose a certain noise model on a good image. And then what they do is they increase the noise. And so if you have noise that is increasing, then you should say that the distributions are becoming more and more far apart. And what they're comparing this to is they're comparing this to Inception Score. So let's look at Inception Score first. So this is what they call inverse Inception Score something, which is really just negative of Inception Score. And what you can see is that as you start to add more Gaussian noise to the image, the Inception Score stays flat, or even decrease a little bit, which is not very good. And you can say that this is because our modern classifiers, due to the fact that we train it with so much randomizations, it's actually very robust to different noise. So if I give it an image and I add some noise to it, your classifier is probably going to tell me the same thing, as long as it's not adversarial noise. And this is reflected here. So we can clearly say that this is a much worse image than the first one, like much less faithful to the original one. But Inception Score doesn't really capture that. Whereas if you use FID to measure this, what you can see is that as you increase your Gaussian noise, you actually get larger distances. So what that means is that this metric is able to capture this kind of noise. And then they do a similar exercise for a couple of different noise models. So in the second row, what they try is they try to add Gaussianization blur to it. And then as you can see that as the distributions become more blurry, the distance increase, which also correspond to our intuitive notion of like the distributions are farther apart. And similarly for Inception Score, just because of the fact that it's a little bit blurry, it can still tell that this is a human face or some other things. It doesn't really change the Inception Score a whole lot. So these are all failure cases of Inception Scores that can be captured by FID. Yes?
So like, isn't this saying that it would give it a high, like FID would give it a higher score if there was Gaussian noise applied to the images?
Well, so FID is a distance. So we want to minimize the distance between two distributions, which is why we are looking at negative Inception Score here. So both of them, we want, as the deviation becomes larger, we want the distance to be high, and we want the negative Inception Score to be high. So basically, ideally, we should always be looking at an increasing curve when we look at as we increase the noise. So there's some other things like drop out some parts of the images. And this is even a more interesting case. So in the second row here, what they did is they tried to basically compute the distance metric on a phase data set. And then they would start to inject some random images from other data sets. So you see that initially it's all faces, and then later you try to inject images that are from CFAR or ImageNet. So this is funny, right? Because like if I have a generator that is trained on faces, I don't expect it to generate cars for me. But if your generator somehow is doing that, then in Inception Score will give you a higher score, because now you're generating more semantically diverse objects. So Inception Score will give you a higher score, and as such, like lower negative Inception Score. But this is kind of wrong, because like I want my GAN to model faces, like I don't want it to model other things. But that part is really not captured by Inception Score, just because it's kind of fixated on the predefined label classes. But for FID, on the other hand, because you're comparing the empirical feature space distributions between your generator to a held out data set, you can actually compare these two data sets. And if my held out data set only has faces, then it would say, as you start to introduce more classes, like it would create larger distances, because like you start to deviate from your validation data. So what this tells us is that FID would very likely capture more nuances, more details than Inception Score can, and it's being used by more papers, but at the same time, it's still not a perfect metric. Yeah.
So FID is clearly much better than Inception, but it's only comparing like second order statistics of
Yeah.
features, right?
Yeah.
Which is sort of what style transfer does as well.
Yeah.
So in that case, is FID at best no better than style transfer kind of loss?
So the comment is around like FID similar to style transfer in the sense that it's looking at up to first and second degree of order of statistics. So I think that's a fair comment, and I think that's probably I would say the biggest attack you can create for FID. That is like you can create high order distributions that have high order of interactions that are not captured by just first and second order of statistics. Like you could construct distributions that have the same mean and covariance, and yet still these two are completely different distributions. So that is true. So I think like likely if you train your GAN by directly optimizing FID, you would get something like that instead of like actually learning the true distribution. Questions on evaluations of GANs? Okay, I would turn it over to Aravind to finish the rest of the advanced GAN methods. Yeah, we can post it now.
I don't even bother clicking it.
Cool. Yeah, let me like quickly recap DC GAN or WGAN and continue towards the rest of the GANs. So DC GANs kind of was a big engineering advance in making sure that GANs can output like really good samples, samples of large resolution bedrooms over large data sets, millions of images, phases, and smooth interpolations, and also ImageNet samples. Even though it's a small resolution, 32 cross 32, the fact that it worked on a large data set was really cool. And you also saw these vector arithmetics across different attributes of faces. And another key result was that you could do representation learning with the discriminator, where you could take the features trained on ImageNet and then use it on CFAR and achieve like really good results for classification. So
Where's the representation learning?
in the discriminator is a connet, so you take that trained on ImageNet and put it on CFAR. So some issues that remain after DC GAN, like even after DC GAN was done, was that the training was still pretty unstable, hacky, and there was a lot of brittle architectural choices. Like you had to use leaky ReLU in one of the discriminator or the generator. I forget which, but you have to use leaky ReLU in only one of them and not in the other. These kinds of things. And also the batch normalization, you have to be very careful not to use it in the output layer of the generator and the input layer of the discriminator. These were very specific choices. And even though a bunch of tricks to improve the training methods were proposed in this paper, it wasn't really super stable. After a while, people thought about connecting some ideas from optimal transport to training GANs, where so far the objective function, as far as the optimal discriminator is concerned, the generator is trying to optimize the Jensen-Shannon divergence between the true data distribution and the generated distribution. So inspired from optimal transport, people thought, what if we could optimize the earth mover distance between the data distribution and the generated distribution. So the earth mover distance is defined in this way, where you're taking an infimum over all possible joint distributions such that its marginals are equal to the data distribution and the generated distribution. And expectation over this joint distribution, distance between the pair of samples. So it's called earth mover because x minus y is some kind of a distance measure, and the probability mass on the point xy is like the mass that you're trying to move from x to y, and by this corresponding distance. So you can think about this as the amount of effort needed to transform a probability mass from one distribution to another distribution. So the goal was to design a GAN objective such that the generator would minimize this between the data and generated distributions. The problem with this particular measure is that it's intractable to estimate, and fortunately they called upon this mathematical duality principle for this particular objective function, such that this infimum over this joint distributions can be converted to a search or a supremum search over one Lipschitz functions, where the objective function gets into the form where there's one expectation for over samples from the data distribution, and another expectation over samples from the generated distribution. So this kind of an objective function is very similar to how you have it in normal GANs, where you have a term for the log probability of the true data samples and the log probability of the fake samples, and you have separate expectations. So this is really cool. So, but still, we need to figure out how to make sure that the search is constrained over these one Lipschitz functions. That's pretty constraining. So that's what the Wasserstein GAN paper tried to do. So Lipschitz, so the definition of a Lipschitz function mapping from x to y, if it's a k Lipschitz function, is that the distance function in the y space between f of x1 and x2 should be upper bounded by this k times distance in the x space, dx of x1 and x2. So the thing is, since we have an objective function here, which is linear in terms of the expectation, we can search over k Lipschitz functions instead of one Lipschitz functions. And then, so the way the authors constrain the search to be over Lipschitz functions is through this argument where they say that assuming that you have a parameterized family of functions fw, where w comes from capital W, if I can ensure that I search over these functions, and one of these functions is guaranteed to be a k Lipschitz function, then I'm whatever max I get over this particular search domain is guaranteed to be less than k times the Wasserstein distance. So why is this important? This is needed because in practice the f that we use for discriminators are going to be neural networks, and you can't exactly make them k Lipschitz, but through some kind of hacks or constraints on what kind of weights they can take or what kind of gradients they can take, you want to use over those weights, we can constrain them to be approximately k Lipschitz. So so that's what the Wasserstein GAN does. This particular line over here is the part that ensures approximate Lipschitzness. Basically, they're clamping the weights to lie between a constant, the magnitude to be not more than a constant c, which is fixed to be 0.01. The reason for this is you can think about if a discriminator is a neural network and has a bunch of weights, you can think about the weight as the gradient for every input. And so if you can constrain the gradient to be between a particular range, then that behaves approximately Lipschitz, because all you want to do in Lipschitz is constrain the slope. So you can think about this as the generalized definition of a slope, dy by dx. So as long as you can constrain it by upper bounding it with a constant, you can ensure some kind of approximate Lipschitz behavior. Yeah.
So we can constrain the gradients by clipping the weights, but why don't we just directly constrain the gradients like negative C and C?
Right. So that's going to be a follow-up. Yeah. Yeah.
The optimizer have to be IMS. Okay.
Right. Yeah. They use RMS prop in this paper.
You have to use it.
I guess if you want to reproduce the results. Yeah.
Was C like 0.01? Is that like chosen for the specific architecture that they used, or like where did they get that from?
It's a hyperparameter for the specific data sets and architecture. Yeah. The rest of the algorithm is very much like the regular GAN, right? You're drawing samples from the generator and real data samples, and this is the objective for the discriminator. And then you take a gradient step on the generator with the negative of this term. The key difference from the regular GAN is that we've gotten rid of all the sigmoids and log of the logits and probability of binary classification. So we saw that those led to all the discriminator saturation problem. Those things no longer exist. These are general. There's no output nonlinearity in FW. You're just constraining it to be the weights to be lying between a particular range.
Mm-hmm. Another question is the learning rates had to be so small, like 5d minus 5.
It's not that small for like general GANs.
Okay.
In general, people, I mean, Andre recommends 3 minus 4, which is what people generally use, but 5 minus 5 is okay. It's not that small. For GANs, it's pretty good. Yeah. Okay. And yeah, precisely the problem that we saw the previous week was that the discriminator gradient would saturate for the sigmoid because gradient of a sigmoid would have product of a sigmoid times 1 minus sigmoid, and whatever is already 0, the gradient would still be 0. So that's what is being shown here. This is the optimal GAN discriminator in the regular GAN. On the other hand, the WGAN critique has linear gradient, so there's no longer the saturation problem. So this is a classifier. This cyan curve is not a classifier, but it only learns to assign high values for one distribution, low values for another distribution. So the gradient is more well behaved. So what does this mean? You can actually train the critique to convergence here. There's no problem with having a converged critique for the generator objective. So you can actually do multiple iterations for n critique, and they use 5 iterations for every generator update. If you do this for the regular, if you remember the previous, the regular GAN pseudocode, even though the pseudocode mentioned k iterations for the discriminator, there was also the k equal to 1 was used. So here it doesn't. You can use more than 1. Cool. And it also seems that the Wasserstein distance correlates with sample quality. So over the training of the generator, the Wasserstein estimate keeps reducing over time. And you can see how the samples also keep getting better. Initially, it's just random noise. Then slowly it gets the scene of the bedroom, and then it starts getting the details. So you can think about the Wasserstein estimate as some kind of perceptual metric. And that apparently turns out not to be true with the Jensen-Shannon divergence estimate. So the key the samples produced by WGAN are on par with the samples produced by the DC GAN, as long as you can optimize DC GAN perfectly. If you use all the hacks recommended by the DC GAN authors and run it on the same data set, you will definitely get good samples. It turns out WGAN can match DC GAN's sample quality. So what's the progress in WGAN if it's just able to do what DC GAN did? The key thing is WGAN is more robust to architecture choices. So if you remember, DC GAN used a lot of batch normalizations. So if you use the same architecture of DC GAN, but you don't use batch normalization, WGAN can still produce reasonably good samples, but DC GAN ends up producing noise. And also, if you change the architecture, so if you, instead of using a ConvNet, if you use a regular MLP for WGAN, so you can see that the standard GAN or DC GAN would, actually you shouldn't call it DC GAN because no convolutions. So standard GAN would end up having mode collapse. You just see a lot of same samples repeated here, whereas WGAN can still output some variety of samples. Yeah.
When you say a different architecture choice, so is that like, you know, at its core, is that like clamping parameter being tuned with the different architecture, or like is it robust to tuning architecture and then hyperparameter optimizing the one thing that WGAN does?
Yeah, I think they use the same set of hyperparameters. Yeah, those. So the summary is that you departed from this objective earlier. You had this minimax loss, log probability of real samples, log probability of fake samples. So you went from this to this Wasserstein formulation where this max is over Lipschitz functions, and you're trying to minimize this difference between two expectations. And like Panda asks, it's likely to be the case that clamping, I mean, it's pretty obvious that clamping is very naive way to do this, enforces Lipschitz constraint. And that was obviously followed up. But that was still, like in terms of robustness, this was a big step. So, let's see. So maybe we can take the break after WGAN GP. So WGAN GP addressed this naive way of enforcing the Lipschitzness, where it uses a more something that works better, rather. That's the best way to put it. So there is a mathematical proposition that's proved in the paper, but we're not going to go through it here. But the conclusion from that is that this was the Wasserstein critique objective that you already saw, and you're trying to maximize over the discriminator. Now, you have an additional term that enforces the norm of the gradient of the discriminator with respect to the input. So these are not gradients with respect to the weights of the discriminator. It's gradient with respect to the input sample that's going in. And you want to make sure that the norm of this is close to 1, where the expectation is taken over points that are obtained by linearly interpolating between real and fake samples. So x and x tilde are from two different distributions. X tilde is from the generated distribution, x is from the real distribution, and this is just a linear all straight lines that pass between these 2 points for different values of epsilon. And you take an expectation over that, and you enforce this constraint on those points. And you can read the paper for knowing why this could be a better way to like enforce Lipschitzness compared to weight clipping. But they have a lot of experimental comparisons on simple toy tasks where there's a data set of 8 Gaussians and 25 Gaussians. And you can see that regular weight clamping wouldn't really capture the data distribution that well, just getting all these squares. Whereas the one with the gradient penalty captures the structure much better, and for the Swiss roll data set as well. And there's also this weight clipping and histogram of the weights under weight clipping and gradient penalty, where weight clipping is just too sparse and concentrated around specific values, whereas the histogram under gradient penalty is much more smoother, more well behaved. Yeah.
What does the linear interpolation of the image space mean? It seems kind of just like
Yeah, it's somewhat connected to the proposition actually, how they actually come up with the approximation to that for the implementation. But it's not super principal. Yeah. So this is the pseudocode for WGAN GP, where the things that are changing from WGAN is that you no longer have the clamping, but the objective function is changed. So the objective function is this. There's this extra term, and yeah, but similar to WGAN, you're going to have multiple gradient steps on the discriminator for every gradient step on the generator. And okay, yeah, the cool thing is now you can do. It seems so they're not using RMS prop, they're using Atom. So if learning rate is 10x bigger, probably can converge faster. And then there's no momentum used in the Atom. Other things are, and the coefficient for the gradient penalty is 10. So these are the default values. And if you actually take this and try to run it on a new data set, it's very likely to work. These are very engineered hyperparameters. Any questions?
Wait, is this n-critic the same as the previous n-critic?
Yeah.
Okay.
It's just a number of times you take updates.
I think it rid of momentum.
Whatever works. Yeah. So this paper took robustness to another level from WGAN. So they benchmark it on different nonlinearities in the generator, discriminator. They also try the soft plus nonlinearity. One important thing to make sure is like the nonlinearities you're trying should obey the fact that you want the function that's output by the discriminator to be approximately Lipschitz. So you want to make sure that the slopes of these activation functions are not super high. They're well behaved. So ReLU has the slope 1. So that's the reason for this weird nonlinearity. And they also try different depths, different number of layers, without and with batch norm for the generator, discriminator, and the number of filters. So all possible combinations of these variations, they tried these different GANs. And it turns out that WGAN GP succeeds a lot of the times compared to the normal GAN. So that's another robustness argument, similar to the WGAN. WGAN GP is a very robust architecture, robust GAN model such that it's robust to architectural choices. So in terms of visible results, you can see how LS GAN, which is another type of GAN, DC GAN, they kind of collapse when you use larger models or different nonlinearities. Whereas WGAN and WGAN GP still continue to work. And WGAN GP works even better than WGAN when you're using like bigger models, like 101 layer ResNets for GND. The samples are really good on the bedrooms. Note that these samples were achieved with larger models compared to DC GAN or WGAN. So it's not the case that everything is good now because of the new gradient penalty trick. It's just that it's easier to train these larger models with the new tricks, and therefore you get even better results. And Pieter introduced these Inception Score metric and the WGAN GP on C410. For unsupervised C410, it works the best. For supervised conditional C410, it works almost as well as the another GAN called stack GAN, which we're not going to cover here, but it was pretty close to state of the art at the time. So the main summary of WGAN GP is robustness to hyperparameters architectures, and it became a super popular GAN model. Like it has like more than 1,000 citations, and only negative of this is the gradient penalty is expensive to calculate. Backward pass, another backward pass basically for every time you want to compute the objective. So it could be having a slow wall clock time, even though you could use faster learning rates and stuff. You might just suffer from just slow training because of the objective function. Cool, we can take a break here now. So yeah, like we saw, this is a robust architecture. So how did it become like very popular? This particular paper is the reason. So this is a paper from NVIDIA on progressive growing of GANs. I think you've seen this idea in pixel CNNs, or I mean in autoregressive models towards the end, when they talked about this idea of upscaling in the color channels and spatial dimensions. So that's kind of what's happening here, where let's say that you have your latent and then you have your discriminator and generator operating at different resolutions. So so imagine that instead of just having a 1 megapixel image and the generator and discriminator trying to operate on that resolution, you have the generator and discriminator operating on all the divisions of powers of 2 of that resolution, 4 cross 4, 8, 16, 32, so on. And the architecture is constructed that way, and you have this multi-scale or multi-resolution loss for both the generator and the discriminator. And so this way the training progresses in a way that you get a lot of signal early on from the smaller resolutions, and that helps you to train on the larger resolutions. Or else it's super hard for you to output these kind of samples without having diverse enough that it makes sense. So these are not real people. They are samples output by this GAN. So that's the level of impressive results that was possible with this WGAN GPU architecture. And I should definitely say that it is not just because of the Wasserstein that all these things happen. There are plenty of upscaling and downscaling tricks that the authors adopted, inspired from graphics or computer vision, such as nearest neighbor upscaling and so on. So the best way to actually understand this paper is to go through the code, because you probably can understand the paper. You don't have to read the archive version of the paper. You better read the code if you really care about the paper. Yeah. So it's not just faces. So I remember when the paper came out, people thought, okay, faces are super easy, but actually that it turns out as long as you can condition on the categories, you can generate these different day-to-day objects. TV monitors, mobile phone screens, cycles, bus, horses, and so on. And the bedroom samples are even larger resolution now, and even more clear and sharp compared to the samples from WGAN GP. Yeah.
So in the previous slide, was the generator conditioned on the noise as well as the?
Yes. Yes. And we'll see how to condition the generator and the discriminator on the class label in different ways pretty soon. And these are 1024 cross 1024 million pixels in these images. And these are the different resolutions at which the generator and discriminator are working, small and so on, size upscaling. So that's all about the Wasserstein GAN. Now we're going to look at another important GAN architecture or GAN algorithm called the spectral normalization for GANs. But the commonality between both what you've seen in Wasserstein and this is Lipschitzness. So let's say that your discriminator is some kind of neural net that does matrix multiplication, activation function, so on, up to the layer L from the first layer. And you're ignoring the bias term for now, but you can have the same math operating for bias. So the discriminator is some function of this neural net, and the generator objective is you're trying to do, the GAN objective is basically have this cost function and play this minimax game. This was changed in Wasserstein GAN to be searching over these K-Lipschitz functions for the discriminator. And the key idea in spectral normalization is that you can look at the Lipschitz constant for every single layer in the discriminator. So every layer in the discriminator neural network would be some function that takes an h in and outputs h out. And the definition for Lipschitz would be the supremum over the singular value of this particular gradient. So you're taking a gradient with respect to the vector of the output with respect to the input. So the singular value definition, if you from linear algebra, is this. Over unit norm vectors, you're just trying to maximize the matrix vector product. And so that becomes a max over h L2 norm less than or equal to 1 of L2 norm of AH. And all this is not taking into account the activation function, because if you're going to use standard activation function like ReLU, the Lipschitz constant for that is 1, so you don't have to worry about that. So another mathematical trick is the fact that if you take composition of two functions, the Lipschitz constant of that is less than or equal to the product of the Lipschitz of the individual functions. So a neural net is basically a composition of different layers operating on top of each other. So if you keep applying this at every layer, you're going to get a upper bound on the Lipschitz of the actual function as a product of all the singular values at of every single layer, and that's just the weight matrix at that layer. So product of all the weight matrices accumulating at every layer would be the would be the thing that you'll have to worry about if you want to constrain the Lipschitz constant of the output function. So what the spectral normalization idea does is it takes the weight matrix, computes this sigma of that matrix, and divides the weight matrix by that value before passing it to the next layer. So this way you can ensure that at every layer you're making sure that the singular norm is the spectral norm is 1 for that layer, and therefore the output becomes well behaved and Lipschitz approximately. Does this make sense? Yeah.
So on the forward pass for every layer, you have to do that.
Yeah.
Oh,
Yeah. I'll actually show you how the pseudocode is implemented further.
oh.
So the question was that how do you calculate sigma? How do you do this every forward pass? So they use something called a power iteration to get an approximate value of the sigma, and luckily it turns out that just one iteration of that is sufficient to implement large-scale models. So just one iteration of the just one power iteration on the weight matrix is good enough that you can implement with standard TensorFlow or PyTorch. Another important difference from other GANs in this paper, spectral normalization, is that they move away from the Wasserstein critique loss or the standard GAN loss and use something called the hinge loss, which you all know from SVMs. But this was first used in this paper, geometric GAN, but to use it in the modern architectures, SNGAN was the first to do that. It's just using that hinge loss, and there's a reason for using the hinge loss. So there's some math that optimizing the hinge loss is equivalent to optimizing the reverse scale, but that's only under certain conditions and not super relevant. But the hinge loss doesn't come out very randomly. And so that's another important change from the Wasserstein critique loss. Cool. Let's see. So the architecture for the generator and discriminator are here. You're going to be using residual blocks all the way through, and the output is a tanh because you constrain, you pre-process your input to be -1 to 1 in general. And the discriminator is basically going to be another big ResNet this is for the unconditional case. And the one way of doing it for the conditional case is somewhere in the middle you fuse the embedding of the class and run the rest of the discriminator. So, but these two architectures are very standard, like ResNet blocks that you do in general for classification, where you keep upscaling the number of channels and reducing the spatial dimension. So why was this paper important? This paper is important because first time you could get a conditional GAN working on the full ImageNet dataset. Till then, like there were some results with some partial subsets of ImageNet, but no, even for a conditional case, no GAN had worked on full ImageNet. So this was the first GAN that worked, done by preferred networks. So you can see how the dogs and pizzas are generated, not the pizzas you had now. Yeah.
How much like improvement was due to the hinge loss versus spectrum normalization?
I don't know if that ablation was done. It might have been done. So you could look at the paper. But I don't remember that specifically being done.
So it seems that this network is really bad at drawing the structure of the dog, like its actual body.
Which one are you?
So on the left, basically all of the
Oh, yeah.
look like nightmare, right?
Yeah, so it's still not that great.
But it seems that they can model faces really well. So if you have a data set of faces, they can model the anatomy of the face really well.
Mm-hmm.
Why is it that faces are easier to model than four legs, I guess?
I think there's more regularity, probably, the data set. Source-centered. The faces data set was constructed by a lot of pre-processing. So that's another thing I forgot to mention. So the progressive GAN result was not just possible because of the architecture, but the authors constructed their own data set called the Celebi HQ data set, where they did a lot of pre-processing on top of the original Celebi data set and made a smaller version of it. So it's possible that in general faces work because there's more structural, the data set is just way more structured and regular, whereas ImageNet is not. But this is not a problem now with the modern GANs, like, or at least it seems like it's not a problem. They're able to generate even dogs very well. I just want to go through some details. So if you're not aware of how batch norm is implemented for con layers, this is an opportunity to know how. If you've not read the original batch norm, you might think that the averages and the variances are taken only over the batch axes, but it's actually taken over the pixels as well to ensure that the normalized filters fire the same way at every location. So the effective batch size in batch norm for con layers is number of pixels times the actual number of elements in your batch. And so I wanted to point this out. So these are your scale and offset, and you just multiply this by whatever standardized version you get from your batch. So why are we talking about batch norm? So there was a question asked on how to use how to train class conditional models. And one important architectural component in all the conditional GANs is the conditional batch normalization trick. And what is that? Basically, you saw that in the previous original batch norm, you're just calling a bunch of free variables for scale and the offset. These are not conditioned on anything. So in conditional batch norm, you're going to condition that on the class label. So the class label, you would get an embedding of the class, and then you would get a linear version of that. You take a dense layer of that and output the scale and offset parameters and use those to adjust your batch normalization. So this way, if you're having a residual block in your generator and discriminator, like in the architecture you've seen here, all these rest blocks will have batch normalization in them. And that batch normalization is now going to take in the class label if it's conditional GAN, and the scale and offset parameters are going to be conditioned on the class label. So you can think about this as ensuring that you let the discriminator and generator know that it's operating on that particular class now, and all these pixel-specific normalizations are adjusted for the class. It's a very important trick, and every GAN, including the latest big GAN, uses it. And this is how it's actually implemented. So there's a small detail. So one thing is these dense layers could be shared at different levels. Like you have multiple residual blocks, and all of them are using batch norm. So you can think about sharing the dense layer for the conditional batch norm on the class label at different levels. And that's a trick that Big GAN uses, which we are going to see now. But I'm sure you all have heard about it. Okay, so we saw spectral normalization. So what spectral normalization does is you can take it a step further, where not only do you make sure that you fuse in the class label for the batch normalization, but you also make sure that this layer uses spectral normalization on its weights. And I'll show you how to use this use a SYN flag, like how it's actually implemented. But basically, it's there everywhere now. So this is the power iteration that I mentioned earlier. It's very simple. So you just want the eigenvalue to be equal to 1. So you just keep doing. So you basically so you have this particular operation where you're searching over this unit norm. So every time you can multiply this matrix by a vector and take the result and normalize it and keep repeating it multiple times. And that's basically what power iteration is. So you have this original weight matrix that corresponds to that layer. You're flattening it such that, and then you take a variable, keep multiplying that with the weight matrix, normalize it, again multiply and normalize it, and so on. So one thing they ensure in the paper is that they don't propagate gradients through these two vectors. So I don't know if that's that's basically a choice for computational simplicity, but in principle you could do it. In principle you could you don't need to have these stop gradients. And then you're finally, after a while, after a bunch of iterations, you're normalizing your weight matrix by this norm value that you get, which is your singular value, and you reshape it to the original shape of the weight. So this is basically how this particular equation is implemented in the discriminators layers. Yeah.
Is this U constant during training?
Yeah. Once you build a graph, it's fixed. There's no dynamic thing going on here.
But then it is possible for the weights to basically be orthogonal to you, right? If they become orthogonal to you, then this computation would not work.
By orthogonal to you mean the dot product becomes 0? Okay. Yeah, it could. I guess in practice it doesn't happen, but or you. So you're saying that this mat mul could become 0, but if it becomes 0, then you just get out, as long as you can make sure that you don't divide with 0, with some epsilon here.
Because it's finding the maximal eigenvalue for the matrix A, right?
Right, but we're estimating it by multiplying it by U, right?
Yeah.
If U is orthogonal to the W, then it doesn't work.
Yeah.
That's the probability for that is really small.
But we're training it, right?
Well, it doesn't need to happen as long as you're initializing it properly.
Because say if your matrix has no non-zero eigenvalue, right? So the space for you to have the space for the 0 eigenvalue is n-1. So it's in the dimension n. So the space for your 0 eigenvalue is n-1. So the probability should be there.
It makes perfect sense to me that when you like initialize randomly your matrix,
Yeah.
then it would
Yeah.
fine. What I'm concerned about is like while training.
Okay.
Yeah.
I guess it doesn't have to.
Yeah.
It could happen actually. So I've never trained this, so I don't know. In fact, like there are some cases in the big GAN where they show the divergence in the training, so it could happen. And how you implement it as part of every dense layer is basically you just have a flag. If you want to use the spectral norm, you just call it, number of iterations, and turns out luckily that you only need one iteration, it works. And they implement it in the same way for convolutional weights as well, but that's in principle not correct because convolution operating on an input tensor is not the same as flattening the kernel and doing a dot product or doing a matrix vector product. There's a different matrix structure for convolution, the Toeplitz structure, so that's not taken into account here. So this is not very principal, but this is how it's actually implemented now. Cool. Any questions on this?
I have a question for the stop gradient. If
Yeah.
they stop the gradient,
Mm-hmm.
yeah, here the stop for U and V, so it cannot. Okay.
Yeah, you just don't want to like learn these U and V's. You're okay with starting.
okay.
Yeah, you only care about this. All right. So this paper got very high quality samples for class conditional GANs at ImageNet scale, and first time we worked something on full ImageNet and has computational benefits over WGAN GP because you don't have to take normal gradients in your objective and take gradients of that. So I just want to mention this projection discriminator trick, but also through that talk about how conditional GANs, different kinds of conditional GANs can be implemented. The first original conditional GAN paper basically implemented it this way, where you just had the discriminator and you fed in the class label in addition to the sample, concatenated them, and learned a neural net that output the adversarial loss. And then there was this paper where that realized that instead of feeding the class table very early on, you can fuse it at somewhere in the middle. So you can process the input, which is an image, through some bunch of con layers, and then feed in the class label embedding. And another paper tried to not have this classification loss on the discriminator in addition to the adversarial loss. So you basically, let's say, it's kind of, you've seen this trick in the improved GAN paper, so it's similar. So there is a classification loss that just regular classifier on the discriminator in addition to saying that the generated sample, whether it's a generated sample or from the data distribution. And finally, there's this trick called the projection discriminator, which is also from preferred networks, where there is a principal reason for doing this, but that's better understood if you read the paper. But the architecture works this way, where you take the input image, you get a embedding from a residual convolutional neural network, you take the class label, embed that, and get another vector for that. And you take an inner product between these two embeddings and add that to the output of this particular small MLP. And that becomes your adversarial loss. In practice, this turns out to work much better than any of the other three cases. And this is now a very standard trick being used in the modern GAN architectures.
The last one means adding the attention to the latent.
It's not attention, but Yeah, some kind of similarity between the embeddings are captured by the inner product. Yeah. Cool. So now the GAN after SN GAN was, which is important to know, is self-attention GAN or SAGAN. So the abstract says why this architecture is important. So it improved the state of the art on 128 cross 128 ImageNet from the Inception Score improved from 36.8 to 52, and the FID reduced from 27 to 18. So these are very big reductions and increases. So, and you've seen self-attention being used in autoregressive models, flow models. So obviously somebody had to do it for GAN as well. And so that's what these guys did. They took a, so this is how the self-attention is implemented. So let's say that this is how it's actually implemented is using a 64 cross 64 resolution. They figure out these 3 feature maps using 1 cross 1 cons, and this is the query key dot product part of the self-attention. And once you figure out the attention values, you add it to the other part with the value part and get the new self-attention feature maps. One trick to do is for one part of the query key value, in this case, let's say you had 64 cross 64 as the input, it wouldn't be scalable to have a self-attention map over like 4096 cross 4096. So what they do is they reduce the height and width dimension and increase the channel dimension for the F and G maps using strides and or pooling. You can do either. And for the other one, they increase the number of channels so that when you finally take the self-attention feature maps, you end up with the same dimension. Again, best understood if you go and look at the code for SAGAN, which is open source.
So they do this like after each like con, they do this self-attention thing?
Yeah, it's part of the architecture. I can show you how it's part of it. Yeah. So mathematically, this is what is happening. So one difference from just regular self-attention is that the scale and offset they're not learning a new parameter for that. So this is just a single scalar value. I don't know why this was a conscious design choice or not, but this is how it's implemented. So that's a single value of gamma for all the dimensions of I and OI, XI, YI. So one thing that I felt was pretty counterintuitive in this paper is that even though the argument for using spectral normalization was to cripple the discriminator or make the discriminator weaker by making it more Lipschitz, they actually apply the spectral normalization here to both the generator and the discriminator weights, not just the discriminator, and it seems to help a lot. Another thing is they use self-attention in both the generator and the discriminator. The hinge loss which you saw, which was being used in SN GAN, is also used here. And this paper is important because just like how SN GAN produced the first full ImageNet conditional samples, this was the first GAN to produce first good unconditional ImageNet samples for GAN. However, it's possible that if you use self-attention and hinge loss on other earlier GANs, it might have still worked. And the conditional models are implemented by using conditional batch norm on the generator and the projection discriminator for the projection discriminator and the discriminator. So that's the way in which you use the class label differently in the generator and the discriminator.
What's the projection?
Oh, the projection discriminator is this thing that, okay. Cool. So these are the visualizations of the self-attention. So I don't know if you can see the difference. These are red, green, and blue. These are 3 query pixels. And you can see that for the red pixel, these are the closest in terms of attention values. These are the closest pixels in the other parts of the image. For the green, these are the closest, and for the blue, these are the closest. So you can see that even though these pixels are neighboring in the original image, the self-attention can attend to like other pixels that are much farther apart and in very different ways for each of them. So, and that's the global notion of self-attention operating here. And in fact, for this dog, you can see that this red focuses on the body, and the green focuses on the background, and the blue focuses on the other leg. So there's a blue pixel query here on one of the legs, and it's attending to another leg here for the dog. So that shows how self-attention is actually helping the GAN to capture a global structure of the image. And these are the different samples. So the conditional samples for different categories of ImageNet, they're all looking really good. Like pointed out in the abstract, the Inception Score and the FID are state of the art, and by a big jump from the previous state of the art, which was SNGAN with projection discriminator. So this was the big, the usage of self-attention and other latest tricks basically made it possible. Finally, the big GAN architecture. Like we saw this in the first lecture of the class, all the interpolations in the introduction. So there's absolutely like no connection to the kind of samples you saw so far, and these samples, these are just too good. And these are high resolution 512 cross 512 samples on the actual raw version of ImageNet. One caveat is Big GAN is a conditional generative model. It's conditioned on the class label. So all these were obtained by feeding in like a particular class label for these categories. And the coolest thing about Big GAN is the interpolations. That's why it became very popular. So you start off with this latent, and you move across and get to this, and you get these smooth interpolations across different classes. So you have these dog and a bird over here, and a dog and a cat over here. So one important trick in Big GAN, which is worth knowing, there are so many tricks, so the best way to distill all of them into your head is read the paper. But this trick is what made a big difference for samples. The first line is this is the orthonormal regularization on the weight matrix. This is another parallel paper published with, along with the SNGAN. This is a different kind of regularization on the weights, such that you basically for every weight matrix you enforce this constraint and make the weights orthonormal. So instead of doing this, they have a mask so that only the off-diagonal elements of this matrix are constrained to be equal to 1, and the diagonal elements are not penalized. Don't ask me why, but there's a reason that this trick is important. If you use this trick, it helps you to do something called the truncation sampling, where in a GAN, let's say you feed in the latents, and let's say the latents are from a Gaussian, and you get the samples. You can constrain the standard deviation to be small. So let's say instead of sampling from a standard normal Gaussian, you sample from a truncated Gaussian. Now, if you keep reducing this truncation so that your Gaussian is narrower, it reflects what you call as a mode collapse, where you just keep getting the same sample. But if you increase the width of the Gaussian, you get more variety. So this has like a width of 2, and you can see different kind of dogs here. And as you keep reducing the width to 1.5 and less than 0.5, you keep getting the same dog again. So and they found out that this truncation trick was only possible because of that particular regularization. And the reason was that if you don't use that regularization and you try the truncation trick, these are the kind of samples you see. Cool. So one more thing I want to point out is that when the Big GAN paper was originally published, they weren't able to train deep models. The models were very wide. They had a lot of parameters, a lot of number like channel dimension in the cons, but the depth of the GANs were not much. The architecture they adopted for the shallower version was to take the latent variable, split it into 3 parts here, and feed them at different levels of the generator architecture. So different residual blocks. You can just think about it as in addition to getting the scale and offset parameters in the conditional batch norm based on the class label, you could also get them conditioned on the latent noise. You could fuse them in multiple different ways. So basically they're feeding in the Z's at different levels of the generator. And this non-local block is the self-attention layer. So someone asked where you actually feed it in. You feed it in the middle when you get 64 cross 64 resolution. And the class label is also fed in at different levels. So this was the architecture they adopted for the original Big GAN. But then they figured out that you can train a deep Big GAN, or Big GAN deep as they call it, by actually concatenating the Z and the right at the beginning, not splitting it, but feeding the same thing everywhere. And that seems to work, modulo some other tricks like how you do the upsampling and downsampling. So usually when you do when you increase the number of channels or reduce the number of channels, you use 1x1 convolutions. But in Big GAN deep, they actually do it in a different way. So if you want to reduce the number of channels, they just pick the first half of the channels, drop off the second half, and there's no learning. So and if you want to increase the number of channels, they just take the existing channels and just predict the additional number of channels from this using a 1x1 and concatenate them. So they have to do these kind of tricks to make it work, in addition to a different kind of conditioning. And this is the architecture of Big GAN deep. This is the generator. This is how a generator block looks like. So when you say rest block here, this is how the rest block looks like in the generator, and this is how the rest block looks like in the discriminator. So this is what I meant by drop channels. And this particular step here is the projection discriminator, where you embed the class label, take an inner product, and add it to the linear version of the previous layer. Cool. The key bits from this paper is that you have to keep increasing your batch size how much ever you can, whatever can fit on your processing unit, and then increase your model size, have wide and deep models, fuse class information at different levels, use hinge loss and the orthonormal regularization and truncation trick. So let's see the numbers. So this was SAGAN, the previous state of the art. This was the FID for SAGAN. This was the Inception Score. And now you can see that the FID and Inception Score in Big GAN are way better. So from 18.65, you drop to 7.5. Actually, for the same resolution, you drop to, if you just want to compare the same resolution, the state of the art is 7.7, and the Inception Score increases to up to 166 or 200. Depends on what you want to look at. Like the combination of both I think it's basically around 126, 166. So that's a big difference between the previous architecture and this. And it also works well at high resolutions, 128, 256, 512, and yeah. So these are the batch size. This is what I meant by training on a larger batch size. So if you keep increasing the batch size, you can think about it as having a large batch, letting the discriminator having a large batch helps you to be aware of mode collapse, but it's not, I mean, the real reason is hard to say. This is a very empirical progress.
Wait, the discriminator doesn't use information across the batch, right?
Because of the batch norm,
Yeah.
class conditional batch norm.
Implicitly.
Yeah.
Oh, I see.
A batch doesn't need to have all samples from the same class. So when you're having embeddings of these class for different samples and they're all fused in different ways, that's so when it's averaging across all of them, it's being aware of what's being fed in. So these are the different samples. You can get dog balls. Yeah. Okay. So finally, I just want to mention the latest advance in GAN called the style GAN. Again, there's a lot of tricks in this GAN, but the main shift from the previous GAN was that just like how you saw that in the previous GAN architectures, the noise is, so in big GAN, the noise is being fed in at different levels everywhere. So that's what the style GAN is also trying to do. But instead of feeding in a single linear embedding of that everywhere, they are basically having a neural net run over the Z for a while and get a vector W for the Z, and they feed these into different levels along with some perturbation noise, and they have something called adaptive instance normalization, which you should check the paper out. So this basically changes the GAN architecture, because the way you think about GAN earlier is you have one Z and then there's a bunch of convolutions, up convolutions, upsampling, and you get a sample. But now it's different. You have a neural net that's just operating over Z's, and whatever it processes is being fed at different levels, along with some perturbative noises, which are very adaptively added based on the batch. So this is what they call as a style-based generator, because it turns out that these different levels can learn different styles. Top levels can learn some coarse styles, and bottoms can learn some fine-grained styles. Yeah.
What's the constant at the top of G? The constant 4x4 by 500.
Oh, that's just a
Some constant.
some constant that could be learned or not learned. It depends on the specifics of how it's implemented. So the samples are just so good. It's so good that people made websites like "this person does not exist," and every time you load it, it'll have a sample from style GAN. So yeah, that's the state of GAN now. You saw how like it's no longer like there's a classifier, discriminator, and all these. So the different architectural changes have made possible like huge advances. A lot of tricks like spectral normalization, self-attention, and so on. So if you want to do like some work on top of these things, the best way to start is GitHub. You have to read the code for all these papers. But note that all these require a lot of resources as well. So Big GAN was done on at DeepMind on TPUs.
Yeah, and GP, and now just like again like a full bag of like tricks that you.
Yeah. Yeah. I think at some point you can be negative about it, but there's other positive ways to think about it too. Like the way Jan LeCun says it is like even deep learning was like that for a while. Like ReLU nonlinearities were very new at some point, and they were considered a trick. And residual connections, batch normalization, all these were tricks, and we're all adopting it as standard practices now. So it could be that after a while we reduce to a small set of tricks that are becoming standard tools that everybody uses. In terms of perceptual quality, the advances you cannot ignore these advances. Like it may turn out that density models are more principal, but the GAN is way ahead in terms of sample quality.
Is there anything we can even improve on this?
Yeah, you can try to do more tricks. I don't know. Usually the way these are written is like the people try hundreds of things and write what worked out. But the nice thing about the big GAN paper is the author also mentions what didn't work. So it's a very good paper to read.
What's the discriminator for style?
Actually, I'm not sure. Maybe you should check out the paper. But I think it's a standard. Okay, let me not say anything. I'm not super sure about it. But as far as I know, the generator is the one that had the architectural update. You've seen the video, right, for style GANs? Yeah. Yeah, I'm not aware of any GAN advance after style GAN, so that's why we stopped here. But it's likely that it happens in a few weeks or months.
So it seems that both big GAN and self-attention GANs use like either non-orthodox or self-attention, or, basically some sort of like instead of just having a local receptive field, they have global receptive fields in practice. Is it better to have a global receptive field in when you're just starting to generate the image at very low resolutions, or is it better to have it at sort of almost the end where you already have a high-res image?
It's a trade-off between that and the computational aspect. So you can't do it at large resolutions because you won't have enough memory to store that tension matrix. So it's only implement. I don't know if you can probably try to do some experiments on that, but so far it seems like all the GAN models are doing it at 64x64, right in the middle. I don't know if people have tried to do some modifications.
If memory were not a problem, would it make sense to have it at high res?
Yeah, it would make sense as long as you have enough computation. You should do it, but yeah, you can try that. You can try that experiment. Cool. So
what's the future direction for the field?
I don't know. Maybe make big GAN work without labels. Like that might be something. As in big GAN level results, but without relying on labels. Or the thing that Pieter Chen mentioned, like having scenes with a lot of different objects. Can all these style GAN like architectures generate that? It seems like faces, bedrooms are doable, but what if there are 4 or 5 humans in a scene, or a human and a cat? These kind of scenes. Can you do it without any inductive bias, or do you need such object kind of like some discrete object latent spaces? Those kind of directions are future. Also, definitely people will keep working on more tricks, more stable GANs. Yeah. Cool. With that, we can end generative model part of the course and move on to representation learning. Let's see. All right. Are you tired of generative models? Or
Yeah, 7 more weeks of generative models.
sorry?
7 more weeks of generative models.
No, this course is deep unsupervised learning. We do things other than generation as well. So, okay, so now we look at something very different from what you've seen so far. So the title is Non-Generative Representation Learning. So what is the motivation to study this? So you know that the ImageNet success happened in 2012, where there was a big reduction from classical vision-based features on the object detection benchmark, object classification benchmark. So, and then over successive years, better architectures, VGG, ResNet, and so on, kept reducing it, and like beyond a point, it went lower than the human baseline. Human baseline is one Andre Karpathy actually. So he just memorized ImageNet in a weekend and benchmarked himself. So now the error is super small. So, however, these relied on carefully curated million labels points, a data set of such size, such scale collected from humans. So that collected from the internet actually. So that's not feasible if you want to like learn from raw samples. And so the motivation is that you want to be able to learn such features even without good labels. So if you have a large data set with good quality labels, and if you can train a large deep neural network, like success is more or less guaranteed. That's something that you can take for granted now. But the point of this part is to make sure that you can do the same, you can generate such high quality features without labels. And how do we come up with these kind of objective functions that allow you to do that is what we're going to look at. I want to take you back to the cake again because you saw this in the first lecture. And so supervised learning is the icing and RL is the cherry. But we're going to figure out how to do the self-supervised or unsupervised part. And the way Jan LeCun talks about it is predict one part of the input from its observed path. So imagine you have like say an image and you're trying to predict the color from the grayscale or the future from the past. So basically you have some inputs, you mask out some of them, you condition on the other, and you try to predict it. So this slide is again from Jan LeCun, where so there are so many different ways in which you can do this. Predict the future from the past or recent past, past from the future, top from the bottom. Anything you occlude and predict from the visible portion. So if you can do this successfully, then whatever features this helps you to learn are going to be general or some representative of common sense. So that's his hypothesis. So today's lecture, we are going to look at different cognitive principles that allow us to do this. The first thing is reconstruct from a corrupted version, for which we see specific instance as denoising autoencoder. Then reconstruct missing portions, image in painting, predict one view from another. We'll see how colorization is implemented. And there are other visual common sense tasks like predicting relative patches, solving jigsaw puzzles in patches, or predicting the orientation of a patch, or doing some tracking from colorization, these kind of ideas. And next week we'll actually look at more ideas which involve like using related entities in the neighboring portions like Vertivec, CPC, BERT, etc. So first, denoising autoencoders. The basic idea is you corrupt your input, you make it noisy, you add different kinds of noise, encode it, and try to decode the actual non-noisy version of it. So this way, you hope that the encoder figures out what's the actual signal present in your input. And this is a figure taken from the original paper. imagine if x is an mness digit, so you can have different kinds of noise. So you can just have a dropout on the input, make it 0, and have the encoder f theta and decoder g theta prime. And you just hope that the predicted z matches the actual x. And the loss you adopt depends on the input nature. So if it's mness, you use sigmoid cross entropy. If it's some other continuous value data set, you can use mean squared error or Gaussian log likelihood. And you can explore with different kinds of noises. So you can have additive noise, Gaussian additive noise, or masking noise where a fraction of them are turned off, forced to 0. They also explore with this salt and pepper noise where a fraction of the elements is set to the minimum or maximum value of that particular input. So this is how it looks like if you want to think about it as a manifold. The true data points are lying on this manifold, on this tangent plane. The x tilde, or the noise that you add, has some particular probability distribution around x or some distortion. And your decoder tries to bring back these distorted samples back to your original data manifold. So this way you hope that this g theta prime and f theta understand the structure of the manifold, because based on the distance of x tilde from the actual tangent to this plane, it has to figure out how much to push it back. So geometrically it has to understand the underlying structure of your data. And one thing you could do in the loss function is you could prioritize the reconstruction of the corrupted dimensions. So you saw that you could turn off some fraction of the elements to be noised out or to be set to 0 over here. So in the decoder part, you could make sure that you're having a higher coefficient for the terms that are actually noised and lower coefficient for the terms that are originally present. And this way you emphasize the denoising part more than reconstructing what's already present. Because reconstructing what's already present leads to the autoencoder objective, and that could collapse to an identity function as long as you have enough capacity in your encoder and decoder. So you want to avoid that. So the paper was actually called Stacked Denoising Autoencoder. The reason is that it was inspired from that earlier work those days in layer-wise pre-training. So you would take an mness digit, figure out an encoder with the denoising autoencoder objective. Now you take the encoder representation of the input, and you don't noise the input anymore, but you noise the encoder now. So you run you mask out some entities in your encoder or add some different kind of noise to your encoder, and then you learn a denoising autoencoder on the encoder representation, and that gives you the second level of the encoder. And if you keep doing this successively, you get the next levels of the encoder based on the denoising autoencoder run on the previous level. So this is what they call a stacked denoising autoencoder, and this is quite representative of work in those days of deep learning, where people would try layer-wise pre-training of RBMs. So you can think about this as layer-wise pre-training of the autoencoder. So why would you do all this? The hope is that if you do it for sufficient levels, at some point you can just stop doing it and add a linear classifier on top and just freeze this, use the representation you got from the stacked denoising autoencoder, and be able to learn a classifier. So the hope is that the stacked denoising autoencoder learn these latent variables that are representative of the class. So these are experiments done in the original paper. I don't know if are you able to see these digit strokes here? Yeah. So if you don't have any noise, if you're running a regular autoencoder, your filters are being very random. But if you add the noise, like say 25% of masking or 50% masking, you start seeing some reasonable filters. And the more noise you add, the more global the filters are, as in the more digit strokes you can see compared to just random perturbations here and there. So this is just zoomed in for these different neurons. And in terms of the classifier, so you just, after you train the stack denoising autoencoder, there are a bunch of different tasks that people constructed those days with MNIST, where they had the basic MNIST, they had a rotated version of the MNIST digits, and one where they used a different background but the MNIST digits, something that you saw in the first assignment. And then other, combinations of all these things. And it turns out that the stack denoising autoencoder can perform really well compared to the models of those days, like deep Boltzmann, deep belief networks, and RBF kernel SPMs, and so on. Cool. So the next cognitive principle is predict the missing pieces. So this was a work done at Berkeley by Deepak Pathak and other people and Alyosha Ifros. So the idea is you take an image, let's say you mask out one portion of it, and you're asked to predict the mask portion. You're asked to output the pixels corresponding to this white mask. And this requires some kind of common sense, because you want to make sure that whatever pixels you fill in here correspond to the window you see here, and so on. So and so you just need to basically look at the background around these pixels and try to fill the rest of the portion inside according to whatever makes coherent sense. So the way it's implemented is you take the image, there's a mask, you can have a 0 or 1, it doesn't matter, and then you encode it, and the decoder outputs whatever pixels correspond to that particular patch that's hidden. You have the true version of it, and you have some loss function that can compare what you output and what is actually true, and you backpropagate that loss into the encoder and the decoder, so that hopefully by the time you're done, this encoder learns some good representations. And you don't have to take the mask at the center portion of the image alone. You can take masks at random locations and output all the random masks that output all the locations that you masked out. And if you have some supervision, some other data set which has boundaries of actual humans or objects in the scene, you could use them and use those masks instead of just taking rectangular masks in different locations. The way you can implement it very easily, if you want to implement these two versions, is that just pick your mask, output the entire image instead of just like one small version of it. So you take whatever input resolution you take, that will be the output of your decoder as well. But you only take the reconstruction loss or any other loss that you want. You only backpropagate the losses corresponding to the pixels that were masked out. So the encoder takes in the unmasked pixels, and the decoder masks out the pixels that you want to backpropagate. And in this paper, they experiment with two different losses. One is using a mean square error reconstruction loss, and the other is a adversarial loss, or as if it's a generative adversarial network. And the key engineering detail is that the discriminator takes in the entire image, but only the generator takes in the masked version of the image. That was because it turned out that for them nothing worked when they fed in the masked and the masked version to the discriminator as well. And now they have a joint objective where there's a GAN objective and the reconstruction of the likelihood objective, and they adjust the hyperparameters such that it works. And this is the architecture where the output of the decoder is fed into the discriminator as well, in addition to having a reconstruction loss. So if this is the input and this is the masked out version, just using the L2 loss will give you a very blurry output here. Just using the adversarial loss introduces some random artifacts, but using both of them ensures you get some reasonable in-painting results here. Note that using some pixel level classification kind of objective, as in a pixel CNN, would work much better than these things. But I think at the time those were not very popular. So, in terms of representation learning, they train on a bunch of images after training this context encoder objective. They try to use that encoder and fine-tune it on ImageNet, on Pascal Walk, the test set as a test set, and they have classification and detection results on Pascal Walk, and segmentation results on the Pascal Walk 2012. So, and it seems like the fine-tuning works reasonably well compared to other baselines at the time, like autoencoder and some other self-supervised objectives, which we'll see. And it also works in reasonable amount of pre-training time. So it ended up learning reasonable representations. Cool. So next is the cognitive principle of predicting one view from another. Actually, denoising autoencoder fits that principle too, because you take the corrupted version, you encode it, then you predict the actual version. So another way of looking at it is you take the raw data, have different views of that raw data, and try to predict one view from the other. And so, for example, let's say you have the input image. Instead of the RGB color, let's say you use the LAB color space. So that's another color parameterization, and it's very useful because the distance in the LAB parameterization, pixel-wise distance, is much more meaningful as compared to the RGB color space. So let's say that you take the L channel separately and the AB channel separately. This is how the image would look like. And you're going to try to predict the AB channels from the L channel, and hope that the encoder that does this and the encoder and decoder that are doing this are going to learn good representations. Does it make sense? So the actual image is looking like this, and you're going to try to predict the AB from the L. And again, L2 regression wouldn't really work here because there are going to be multiple possible AB outputs for one input. So you're just going to get a degenerate output here, which is averaging across all possible outputs. But it turns out that if you use a classification objective, where if you take the AB space, take all the possible ranges in your data set, bin them correspondingly, and have categories for each output. Then if you just, instead of using a mean square error loss, if you use a cross entropy objective, it works much better. And this is in general true in deep learning. As long as you can bin something, you should bin and run a cross entropy loss.
How do you ensure that the nearby pixels are like coherent?
Because the ground truth is like that, right?
But like if you're like high probability of like red and blue birds, then if your like probability distribution is like gives you high mass on blue and high mass on red, what if you predict like red for one pixel and blue for another one right next to it?
Mm-hmm. So your question is, when you're using a factorized decoder, such that the prediction for each pixel is independent of the other, yeah, how does it still learn? Yeah. If you make sure that, actually they have another trick in this paper too, which I haven't mentioned here, which is to make sure that you only you prioritize the predictions of infrequent pixels, as in after you've bin the AB values to a certain specific number of bins, you have priorities for the loss of the AB value based on how frequent it is in your data set. So maybe that's actually helping them. Cool. I think I'll stop here and continue from the rest next week.